So students, welcome to video class 14. So in this video, we are going to study about second order system, or rather the time domain analysis of a second order system. In the previous video, we did the such an analysis on the first order system. Now, how will you differentiate an nth order system? I have given you the idea about the order of a system. The order of a system is governed by the characteristic equation, say that is 1 plus gs h is equal to 0, or the polynomial 1 plus GHSH, which is actually the denominator of the transfer function. So if the transfer function is of the form P of S to Q of S, this represents actually the Q of S. Now this Q of S, considering the Q of S is going to be a polynomial of a polynomial of S, and the order of the polynomial, the denominator polynomial or the characteristic polynomial, will decide the order of the system. Now, obviously, for a second order system, the order of this characteristic polynomial or the equation will be 2, right? And the such a system we call as the order is 2, so such a system we call as the second order system. Now, to start with, as we have started with the first order system, we have assumed that a typical first order transfer function, which we consider as 1 by Sg plus 1. Similarly, we will be starting with by a general expression for the transfer function of a second order system, which is given by C of S to R of S is equal to omega n square divided by S square plus 2 theta omega n s plus omega n square. Okay, so this is the equation. Instead of 1 by Sg plus 1, you have considered your C of S by R of S as this. Now look at the denominator polynomial. Before going into the details of this, let me just prove that this transfer function is a transfer function of a second order system. That is, the characteristic polynomial or the denominator polynomial is having an order equal to 2. So that means this particular transfer function should represent a second order system. Okay, so the order of this transfer function is 2, and which actually describes what a second order system is. Okay, now this let me define this term, and I will be explaining it later what it is. Just to define, where omega n is called as a natural frequency of oscillation of the system. Frequency of oscillation of the system. Theta, say it is represented like this. This word is called as a Greek letter called as theta. Theta. It's not theta, it is theta. Okay, you may just refer the textbook to see the exact notation, right? This looks more or less like this. So the theta is referred as the damping ratio. Okay, so damping ratio. So that means this factor or this damping ratio and this natural frequency are interrelated. You know what is a damping? Damping is nothing but damping is defined as the process of bringing the oscillations to zero. So this is what is called as damping. We call that a damping takes place. So there will be natural. So a system, if it is oscillated, it will be having a natural frequency of oscillation that can oscillate at a natural frequency, and this damping ratio associated with that system will decay that oscillation. Okay, so these are the two parameters that we can see, or the two parameters that you can see in this second order transfer function, where I again repeat, that is, it is Cs by Rs is equal to omega n square by a square plus 2 zeta omega ns plus omega n square. So where omega n is the natural frequency of oscillation. That means if the system oscillates naturally, then that will oscillate at this frequency, while the zeta is the element which is also a characteristic of that system, which will make this frequency of this oscillation to nil, or which will control this oscillation. So these are the two parameters that you can come across in a second order system. Okay. Now, our next aim is to convert this transfer function into its canonical form. Okay. So this is into a canonical form or in the closed loop. How can you realize this? This is the transfer function. From this transfer function, can you make this transfer function of the form g of s by 1 plus g as hs? Now, if you can make this in this form, you can very well represent that system as system shown here, right? Okay, so there will be a feedback, and that will be h of s. Okay, since it is plus, this will be minus, and this is r of s, and this is c of s. So our aim is to using this transfer function, can you convert this transfer function into its canonical block diagram? So for that, what you do is I'm going to do some manipulation on this transfer function. Say c of s by r of s is equal to keeping that omega n squared as such, and in this equation I'm taking this s square plus 2 zeta omega n s outside, s square plus 2 zeta omega n square outside, so that you will get this as omega n square divided by s square plus 2 zeta omega ns, right? Okay, so now you can bring this, now you can have a reshuffling of that is omega n square divided by s square plus 2 zeta omega ns, right, the whole divided by 1 plus omega n square by s square plus 2 zeta omega ns into 1, right? So now look at this. This corresponds to, this one corresponds to g of s, right? So this is your g of s. So you have a g of s here, right? G of s into 1. So this is of the form g of s by 1 plus g s h s. So here you can write this g of s to be omega n square by s square plus 2 zeta omega ns, while h of s to be equal to 1. So this represents, this actually represents a unity feedback system. So that can be represented by the block diagram as shown. Okay, look at this. So this is your block diagram. You have your g of s. G of s is represented as a block, and h of s is 1. So this is actually the block diagram representation of a second order system whose transfer function, whose general transfer function is given by c of s by r of s is equal to omega n squared by s squared plus 2 zeta omega ns plus omega n square. You should study this by heart. So this is very important. So these two equations, these two transfer functions, this is the transfer function of the first order system, this one is a transfer function of a second order system. You need to know it by heart. So learn this and try to understand each parameters. Okay. Now let's see the time response of a second order system subjected to a unit step input. That means you're giving a unit step input, that is your u of t, or your r of t is equal to u of t, meaning r of s has to be 1 by s. So what you're going to give, so if you consider this as a single block diagram, what you are going to give this to the second order system is r of t or u of t, and you're going to find out your response c of t, right? So you know the transfer function. The transfer function, this is a second order system, and the second order system transfer function is already given. So if you know the transfer function, if you know the input, you can find out this output, right, from this transfer function. Now what is this? This is actually the time response. That is, you are going to find out time response, meaning you're going to find out the c of t for a second order system when you give the input u of t. Or in other words, this is nothing but this is the step response, right? This is the step response of a second order system. Step response of a second order system. So this heading can be rewritten as step response of a second order system. That means what you got is r of t is actually u of t, right? So that means r of s is equal to 1 by s, which is nothing but it is the Laplace transform of u of t. We know that from we have just learned that the general transfer function of any of a second order system is given by omega n square by s square plus 2 theta omega ns plus omega n square. Okay, so I just told you what is this omega n and theta. Will come this during during the course. We'll be explaining more about omega n and theta, right? Now what is this r of s? R of s is 1 by s, so that you can have this c of s is equal to, this can be replaced by 1 by s, bringing here you can have the expression 1 by s into omega n square by s square plus 2 theta omega ns plus omega n square. Okay. Okay, now to continue our analysis, I am going to do some manipulations on this term, that is s square plus 2 theta omega ns plus omega n square. Okay, now you know what is this a plus b the whole square. So I am going to represent this in the form of a plus b the whole square. So I'm just evaluating, say, s plus theta omega n the whole square. If you expand this, that is, this is a plus b the whole square, which is equal to a square plus 2ab plus b square. So you can see that this will be s square plus 2 theta omega ns plus theta omega n square. Now from this, you can evaluate what you can say. You can represent this s square plus 2 theta omega ns as what? So from this equation you will get this 2 theta omega ns as equal to s plus theta omega n the whole square minus theta omega n the whole square. Hope you understood. So bringing this term to this side, you can represent this much as this. Okay, rewriting that, you will get it as, so okay, you will get this as omega n square by, instead of s square plus 2 theta omega n, I'm substituting this. So we'll get this as s plus theta omega n square minus theta omega n square plus this omega n square. Now you can combine these together as shown. So in the next step it will be 1 by s into omega n square divided by s plus theta omega n the whole square plus, taking this omega n square from these two, you will get this as 1 minus theta square. 1 minus theta square. Okay. Now next step is what we do is, when you get a c of s like this, so you can do this, you can resolve this in partial fraction, right? So you can resolve this, and this is a quadratic term, right? This is s square plus something. So this is a quadratic term, so you can make use of this. This can be equated as a by s plus b s plus c, right? This is how you take the quadratic term. So writing that quadratic term as such, as n the whole square plus omega n square into 1 minus theta square, right? Now you may do that Now you know how to, so this is equated to this, right? Now what you need to do is you need to multiply the whole equation throughout this term. So this one is equal to, so this fraction is resolved as partial fraction, right? So what you need to do is you need to multiply this whole of this denominator throughout. That means this becomes omega n square. So while doing, you will get omega n square is equal to a into this thing plus bsc plus c into s, right? That's how you will be getting. So you can do the rest of the thing by yourself, and you will be getting this a to be equal to 1, while b as minus 1, and c, you're going to get this as minus 2 theta omega n, right? So you may just do it by yourself to check whether you'll be getting this these values for this. A is equal to 1, b is equal to minus 1, c is equal to minus 2 theta omega n. So using this, now substituting this in this equation, you will get, okay, now while substituting, you will get this as 1 by s minus, so a by s, 1 by s, and you are putting this minus throughout, so you can take this outside. So this becomes s plus 2 theta omega n divided by s plus theta omega n the whole square plus omega n square into 1 minus theta square. Now from this, I am going to introduce one more term. Say, what is this? This is actually, I am rewriting this again, this term omega n square into 1 minus theta square into 1 minus theta square, and this I am calling this as omega d square, or from this you will get omega d as root of omega n square into 1 minus theta square, or this is equal to omega n into root of 1 minus theta square. Now where this omega d is called as what? Omega d is called as the damping frequency of oscillation, frequency of oscillation. Okay, what is this omega n? Omega n was called as the natural frequency of the oscillation. This is the way in which the system, if it oscillates, it oscillates naturally with this oscillation, if there is a sustained oscillation. And this damping frequency is again a characteristics of the system, and that depends on this damping ratio theta. So based on this damping ratio, you have another set of oscillation. Now how to reduce, basically how to reduce an oscillation? Say for example, I will just give you an example of this. Say suppose you have an oscillation like this. Now how to reduce this oscillation? Now if you can give a reverse oscillation like this, right, effectively what happens? This reduces to 0, right? So at the very moment, if you can, in the reverse direction, that's the, I just made you understand the concept of this damping. Okay, so there must be a reverse operation in the form of damping, or which actually reduces this natural frequency to 0, thereby preventing the system not to oscillate. And basically, as far as a stable system is concerned, what our main objective is to reduce the chance for the system to oscillate. So this parameter is going to be a very important parameter as far as a second order system is concerned. And I again repeat, this omega d is what is called as the damping frequency of oscillation, and that is given by omega n into root of 1 minus theta square. Okay, now mark this equation as 1, this one as equation 1. Now we will resume from this equation. to find out what's our main objective. You should not forget that the main objective is to find out the step response of the second order system. That means when you give u of t as the input to the system, we are going to find out the c of t. We already have your c of s, and you just need to find out the inverse. Okay, now let's see how to find the inverse of this so that you will get c of t, and that is what is required. Okay, now from this equation 1, what we are going to do is we are going to split this. Now 2 zeta omega n can be written as zeta omega n plus zeta omega n. So rewriting in that fashion, you will get your c of s as, okay, c of s as 1 by s minus s plus, right, s plus zeta omega n, right, zeta omega n plus again another zeta omega n. So this is, when combined, you will get 2 zeta omega n divided by the whole thing, s plus zeta omega n the whole square plus omega n square into 1 minus zeta square, right? Now you can rewrite this expression as, okay, you can rewrite this expression as, so this will be 1 by s, okay, minus, you can take this term, so this is, this you can split as 2 s plus zeta omega n divided by s plus zeta omega n the whole square plus omega n square into 1 minus zeta square, okay, minus, you have again zeta omega n divided by s plus zeta omega n the whole square plus omega n square into 1 minus zeta square. Okay, so hope you things are clear. It is just you are taking this term away and this just split into a suitable form. Okay, so this is it. Now look at this. So c of s can be written as 1 by s minus, I'm going to rewrite it again, so zeta omega n divided by s plus zeta omega n the whole square plus, these are all zeta now. Okay, you may just refer the textbook, again I repeat, to see the real shape of this okay, then of this character. So this is omega n square into root of 1 minus zeta square. So we have just introduced a term called as a damping frequency of oscillation. You can replace that by omega d square, right? Omega n square into root of n minus n square can be written as omega d square, right? Omega n square into 1 minus zeta square is omega d square. It is the square of the damping frequency of oscillation. So you can represent that term as omega d square minus, say, zeta omega n divided by s plus zeta omega n the whole square plus omega d square, right? Okay. Okay, now our next aim is to find out c of t. Okay, when you take the inverse of this, this will be 1, and this term is also having no problem because this is of the form s by s plus, so this is of the form s plus a by s plus a the whole square plus omega square. You may be remembering that s plus a by s plus a the whole square plus omega square is nothing but it is actually e raised to minus at into cos, okay, cos omega t, right? So this is of the form. Now this term is similar to it's having all these things, but it doesn't have any s. And if it would have a term like say, if you have a term like this, omega by s plus a the whole square plus omega square, then you can write this as e raised to minus at into sine omega t. Okay, you might have studied this, right? So now the omega corresponding to this term is omega d. So there is no omega d, so you cannot directly convert this into a sine term. But you can do a manipulation, right? You can just multiply and divide this term by omega d, so that now this omega comes over here, so that you can convert this into what? Into the corresponding sine function, e raised to minus at. So doing that, so you will be getting your c of t as the inverse, so that is equal to 1 minus e raised to minus theta omega nt, right? Nt into cos omega dt, right? Cos omega dt, cos omega dt minus, you have a theta omega n by omega d, right? So you have a theta omega n by omega d into, what is this called? This is actually e raised to minus minus theta omega n into t cos, sorry, sine omega dt, right? So this is sine omega dt. So this is 1 minus e raised to, I repeat, e raised to minus theta omega n into t into cos omega dt minus theta omega n by omega d. Do remember, you have an extra term into e raised to minus theta omega n t into sine omega dt. How come this omega d? That is to convert this expression into that of a sine. That's why we put a numerator and denominator by omega d. So you got this expression to be like this. Okay. Now listen please. So we have just learned the relationship between omega d and omega n, that is equal to omega n into root of 1 minus theta square, right? Omega d into root of 1 minus theta square. Now what is this omega d by omega n? Omega d by omega n is root of 1 minus theta square, right? Okay, so what will be omega n by omega d? So from this you will get this omega n by omega d to be 1 by root of 1 minus theta squared. So you can convert this as 1 divided by, so you can replace this omega n by omega d by this term root 1 by root of 1 minus theta squared. So doing that, you will get this c of t as c of t is equal to 1 minus, now I'm going to take this term, right? This term so okay, I'm just rewriting this, e raised to theta omega n into t cos omega dt, okay, omega dt minus theta divided by, what is omega n by omega d? Omega n by omega d can be replaced by 1 by root of 1 minus theta square. So this will be root of 1 minus theta square, right, into e raised to minus theta omega n t into sine omega dt, right? Now what you can do is, in the next step, what you do is 1 minus, you are taking this e raised to minus theta omega nt and this root of 1 minus theta square common. Okay, so you have an e raised to minus theta omega nt on both sides. So on the both term, so it will be e raised to omega nt divided by root of 1 minus theta square into, so this will be root of 1 minus theta square into cos omega dt minus theta into sine omega dt, right? So you are taking what happened is, you are taking e raised to minus theta omega t and this thing outside, so there is no root of 1 minus theta square, so it comes over here. So this will be root of 1 minus theta square into cos omega dt minus theta. This is not 1, this is theta into sine omega dt. Okay. Okay. Now what I'm going to do is I am assigning these values, that is root of 1 minus theta square and theta, to another cos function as, that is simply put, sine phi. So put sine phi is equal to root of 1 minus theta square, while cos phi as equal to theta, and you will understand what is the implication of this phi after a while. Okay, rewriting that now, substituting those in this equation, call this equation as equation 2. So substituting in 2, we get your c of t to be equal to 1 minus e raised to minus theta omega nt divided by root of 1 minus theta square into, what is this root of 1 minus theta square? Root of 1 minus theta square is sine phi, right, into cos omega dt minus, what is the theta? Theta is actually cos phi. So this is cos phi into sine omega dt, right? So this is of the form sine A cos B minus cos A sine. Now using that identity, you can convert that as, okay, there is a correction here. It is plus because you are taking this minus common outside, right? So this is plus, so this will be plus, and this one will also be plus. So what you can write this for, sine A cos B plus cos A sine B, which is nothing but it is sine A plus B, right? So using that identity, you can rewrite this expression as c of t is equal to, c of t is equal to 1 minus e raised to minus theta omega n into t divided by root of 1 minus theta square into sine omega dt plus phi, right, where omega d is already, we have defined omega d as omega n into, omega d is omega n into root of 1 minus theta square. And what is this phi? You can, from the sine phi is assumed to be equal to root of 1 minus theta square, cos phi is equal to theta. So why can't you take sine phi by cos phi? So taking sine phi by cos phi, you will get this as root of 1 minus theta square by theta square by theta, right, by theta. This is 1 minus theta square divided by theta, 1 minus theta square by theta, that is sine phi by cos phi is equal to root of 1 minus theta square by theta, which is actually equal to tan phi, right? So from this you can come to a conclusion that this phi is nothing but phi, or I'll write here, phi is tan inverse, what? Tan inverse root of 1 minus theta square divided by theta, right? So this is it, right? Okay, now we got your c of t as 1 minus e raised to minus theta omega n t divided by root of 1 minus theta square into sine omega dt plus theta plus phi, sorry. So this is actually valid for theta less than 1, right? So that is it. Theta lies in between 0 and 1. Okay, theta is a positive quantity because that's a damping ratio, so ratio cannot be a negative value. So this is theta, so theta is going to be less, I mean, as long as theta is, so this is valid. This equation is a case where 0, where theta is between 0 and 1. The reason I told you, because we have assumed this theta to be what, cos phi, right? And okay, so when theta is assumed to be cos phi, meaning that since we know that cos phi varies from -1 to +1, so anyway, cos phi, since it is cos phi, but we take the theta as a positive quantity, that means we'll take only 0 to 1. That doesn't mean that theta can't have a value greater than 1. Yes, it can be greater than 1. In that case, we cannot use this equation, because we got this equation under the assumption that cos phi is equal to theta. Now when theta is greater than 1, this equation is no longer valid, so you will be having another expression for theta greater than 1. So for mind you that theta is a positive quantity, this is an equation of the step response for theta lies in between 0 and 1. And again I repeat that theta is nothing but it is the damping ratio. It is the parameter. This is the parameter which determines what? Which determines the damping, the amount of damping, right? So the damping, so that it nullifies the oscillations, the natural oscillations that occur in a system. Okay. Now what is this called? This is called as the step response of a second order system. Okay. Now we understood that the step response depends on the value theta. So theta, as I told you, the theta is a positive quantity that can have various range of values. That can be 0, that can be 1, or that can be in between 1. And I told you that this equation is valid if theta lies in between 0 and 1, or it is equal, it is in between 0 and 1. For theta greater than 1, this won't stand, because of the fact that we have assumed cos phi to be theta, right, in this case only. So that means there can be 4 different cases. This is one among the case, and now the 3 cases will be, we will be using this equation for finding out the c of t at theta equal to 0, then what happens when theta is equal to 1, and what happens when theta is greater than 1. These are the other 3 cases that we will be dealing after this. Okay, so we'll start with the case where theta is in between 0 and 1. That means this equation is valid. And now we are going to draw the step response. Okay, now what is this c of t at t is equal to 0? So anyway, we want to draw the graph. If you want to draw the graph, as you all know, that you need some points. So this is your t, this one is your c of t. So at t is equal to 0, what happens? So at t is equal to 0, substituting t is equal to 0 over here, this becomes 1, right? So this is sine 0 plus 5, or sine phi. Okay, so when you substitute this, you will get this as 1 minus, this part becomes 0, this part becomes 1. So this is 1 by root of 1 minus theta square, right? 1 minus theta square into sine omega. This is 0, but sine phi, that is into sine phi. Now what is the sine phi? As long as theta lays in between 0 and 1, the sine phi we have assumed to be root of 1 minus theta square. So substituting that, 1 by root of 1 minus theta square into root of 1 minus theta square, right? So this and this will cancel, so this is equal to 0. So we know that the c of t at t is equal to 0 is 0. Now what happens? So actually what you are expecting to this output is, you are as I've told you earlier, so you are giving an output u of t here, right? And what you are expecting in the output is this, but you are not going to get that, because at t is equal to 0 we found out to be it is equal to 0, right? Now what happens what happens to the c of t at t is equal to infinity? When you put t is equal to infinity, since this is e raised to minus infinity, this becomes 0. So that means your c of t becomes 1. So if you mark the c of t as 1, right? So anyway, we know that this is going to reach at 1, right? But you may be feeling to draw something like this, right? Okay, so that's not true, because this would have been this we have studied in our earlier study when we dealt with with what with the step response of a first order system. So this is actually for the function 1 minus e raised to minus t by t. But in this case, you instead of that, I mean, along with this exponential signal, you have a sinusoidal function as well. So this anyway, this function is not going to behave like this. So had it been there, I mean, if there would have been only the exponential signal, then you can expect a signal like this. So that means this is not the way. This is not the way in which this output looks like. So because of the fact that that there is a term, sinusoidal term. So what do you expect that? So the real this thing I will draw by another ring. So I'll use a green ink. So it would be like this, right? It will be going in this way. And why this? This is due to this sinusoidal function. So there is a oscillation at the output, but what happens? It reduces to 0 at reduces to 1s, right? So there is an oscillation, and oscillation finally damps. So this is, even though there is an oscillation, this is what is this is called as damping. And the fastness of damping is depends on this damping factor that ranges from 0 to 1. Okay, so this is how it is. So so how do you draw this? I mean, this is not exponential in nature. Why? Because it doesn't, it not only has the exponential signal but also have a sinusoidal signal. So as time increases, yeah, there will be an oscillation, but because of this exponentially decaying function, so it is this function is the decisive function which actually nullifies that oscillation. If there would have been no this function, we will see that later. Because of the absence of this, then there will be oscillation, or the system can tend to an unstable state. So in this case, so that is what I'm going to say. What I intend to say is that for a second order system subjected to a unit step response, as long as your zeta, that is the damping ratio, lies in between 0 and 1, even though there is oscillation at the output, it will reach at the desired value of 1 after some time, and that results in damping, and this condition we call as the under damped condition, right? So this is under damped condition, where and the condition is dictated by the value as zeta varies from 0 to 1. Okay, now I'm going to define something called as a time constant of a second order system. Time constant of it. Okay, so I'm going to just write an equation which you have studied in your e raised to minus r by L into t. You might be remembering that this is actually the the response of a RL circuit. So you have an equation like this, and you have defined this t to be L by R, right? So there you define this time constant to be L by R. And what is the significance of this time constant? Time constant is a time that, I mean, you can define this also in this way, apart from that percentage definition. That is, it is the time that makes this exponential term unity. So when this exponential term becomes unity, that when time becomes equal to L by R. So if you go in that way, how will you define the time constant of this second order system? We know that this is the equation for the step response of of a second order system. And at what time this e raised to minus zeta omega nt becomes e raised to minus 1, or at what time this becomes unity? We know that from this, we know that when t becomes equal to, when t becomes, that is your capital, when t becomes is equal to 1 by zeta omega n, or this is what is called as a time constant of the second order system. Now, that means this decaying, right? You know that this decaying is exponential in nature because the decaying is determined by this exponential signal, and the rate of decaying is governed by 1 by zeta omega n, which is actually called as a time constant, right? Now, the how faster it must be, it depends on zeta, right? So so that means this is 1 by zeta omega, and so the time constant can be, so the time constant will be can be greater, right? So what happens when zeta is less, I mean it's closer to 0, that 1 by zeta omega n becomes a high value, right? So as it becomes a high, that means it will take too much time to damp. So that's what I told you, that the time actually depends on this zeta. The rate of damping depends on this damping ratio. Okay, so that's it. So that's called as the time constant. It is given by 1 by zeta omega n, right? Now one more point is there, that is now how to find out the error. I told you that the error E of t is nothing but it is r of t minus c of t. When you do this, so you know this r of t is 1, right? The input that you gave is 1 minus this c of t, you will be getting this as 1 minus e raised to minus zeta omega n into t divided by root of 1 minus zeta square into sine omega dt plus phi, right? Okay, so this is it. As I told you in the last video, that the steady state error is the, that is I want to find out ESS of t, that is called as the steady state error, or this is actually the error at t tends to infinity. Now when you put t tends to infinity, what happens? We already found out that c of t becomes 1, or in a sense that this becomes 1 minus 0, or this is equal to, this becomes 1 minus 1, which is equal to 0. So this term vanishes, right, as theta becomes in, as t becomes infinity. So this is 1 minus 1, which is equal to 0. So the steady state error for a unit step to a second order system is again 0, just as we studied in the case of a the step response of a first order system, right? So in the first order system also we found out the steady state to be equal to 0, steady state error to be equal to 0. In the second order system also we found this steady state error to be 0. And okay, so hope you understood this. Okay.